Hi everyone, my name is Aman Saini and I'm a machine learning engineer at Grammarly. I'm here to present Spivavtor, which is a set of instruction-tuned text editing models for Ukrainian. This is a joint work by research scientists and machine learning engineers at Grammarly. So let's talk about what is Spivavtor. It means co-author in Ukrainian, and it's a collection of text editing models which have been instruction tuned to perform text editing in Ukrainian. We have trained these models on a curated dataset, which we have also open sourced as part of this work. Spivavtor can perform 4 types of tasks today, starting with grammatical error correction to simplification, coherence, and paraphrasing. The reason we picked these 4 tasks is because we think that they are largely representative of the most common types of text editing tasks, and it was easier to find data in either English or Ukrainian for these tasks. But Spivavtor is a Ukrainian model. It takes instructions as well as the input in Ukrainian and outputs in Ukrainian as well. Spivavtor models are very closely related to the previous work, which is CoEdIT and MEdIT models released by Grammarly. Now, what can Spivavtor do? So on the left-hand side, or the first column here, we see that for the 4 tasks that Spivavtor can do, we input to the model an instruction followed by the input text. The model actually learns to apply the instruction on the input text and in return gives us back the output text. So the instructions basically are specific to the task at hand, and they look like simplify this sentence or rephrase this sentence or correct the grammar in this sentence, etc. And these instructions are followed by the actual user text, which the model then applies the instruction to. So this is actually an example from the actual model's output, one of our best performing models, basically. Now let's talk about why did we build it. So there has been a lot of previous work in the Ukrainian LLM space in the past few years, but most work has focused on either of these 3 categories. The first one being many models are very task specific. So even though there are models for grammatical error correction or formality transfer or style transfer and named entity recognition, for example. So task specific models, but we couldn't find many multitask text editing models. The second one being that there have also been models which are more general purpose instruction tuned models rather than specific to text editing. So models like UNLP are examples of such models which were trained using a diverse set of instructions rather than a task-specific instruction, for example. And then the third category is that there are many multilingual models which actually focus on text editing, for example, MEdIT, but many of them actually do not consider Ukrainian as part of their languages. So hence we found the need to actually build a multitask instruction tune model for Ukrainian. Let's talk about the data set first. So there have been a lot of other types of text editing data sets like pause tagging and data sets for word embedding, question answering, sentiment detection, text generation data sets, but we couldn't find a lot of text editing data sets, and hence we curated our own data set for this, which we call as Spivavtor-Instruct. Now, this data set consists of 2 types of data. One is the actual Ukrainian data, which is what we use for grammatical error correction task. There is a publicly available GitHub repo where UAGEC dataset is shared, which is exactly what we use for our grammar and fluency task. And for the rest of the 3 tasks, we actually translate our English data sets that we used for other models like CoEdIT into Ukrainian using Google Translate API. And here are some of the data sets that we have used for training, which is also open sourced. Let's talk about adding instructions to that data, because just having an input-output pair doesn't allow the model to actually get instruction tuned. So we append instructions to each of these input-output pairs, but just to the input side, so that the model knows exactly what to do. And we call them verbalizers. These instructions were actually curated by native Ukrainian speakers, and we use many verbalizers for each task just to increase model's robustness. Here is just an example of a few instructions that are being used. In the second column, we've put the English translations next to it, but they are only for reference. The actual instructions that the model takes are in Ukrainian. Now, this is the dataset size that we have open sourced, about 60,000 or so training examples, and about 10,000 or so of test examples, and 40 verbalizers in total across all the 4 tasks. Now, talking about the models, we explored models in 2 different dimensions, one being the model architecture, which is the style of model, for example, an encoder-decoder style or a decoder-only model. And the second dimension is the model size, starting from 1 billion all the way to 13 billion parameters. And needless to say that all the models that we have used here are multilingual with support for Ukrainian. This is the list of models that we have picked for our evaluation. Talking about encoder-decoder models, we've used MT5, MT0, which are the encoder-decoder models that we all are widely popular and we all know about. And we have also used Aya here, which is a model by Coherence, which has Ukrainian listed as one of its medium resourced languages. And it actually significantly performs better than the MT0 models. And for the decoder-only models, we've considered Bactrian, which is a set of low-weight adapters which are trained using LoRa, built on top of Llama, and followed by like Mistral's model, as well as the full-scale fine-tuning for our Llama 2 models released by Meta. Regarding training and inference, we use 8 A100 GPUs with an effective batch size of 64, and we've tried multiple learning rates and finally settled on the ones using our validation cross-entropy loss and a sequence length of 512 or 256 depending on the style of the model. Now let's talk about evaluation. For evaluation, we compare against the following baselines. The first baseline is the copy baseline, which is when we actually assume no edits have been made to the input, and the model, basically this baseline outputs exactly the same input, followed by UAlpaca. UAlpaca is actually a Llama 7 billion model, which has been trained on Ukrainian instructions of a large, diverse set of instructions. And the reason we take this as a baseline so that we can compare the effect of very task-specific instruction tuning against large-scale, diverse, general-purpose instruction tuning. And then following the industry, we also compare against ChatGPT and GPT-4 style models. And we are aware that the performance of OpenAI models is very sensitive to the prompt, and hence we report the best results here that we have achieved by playing with the prompts. These are the test sets that we have used to evaluate across all the 4 tasks. For GEC, we do have a Ukrainian test set that has been publicly released as part of the GitHub repo. And for simplification, coherence, and paraphrasing, we use the Ukrainian translations of English datasets for evaluation. Now, talking about metrics, for GEC, we use F0.5 correction score, which is similar to an F1 score with precision being weighed twice as much as recall. And this is a widely popular metric which is being used for evaluating grammatical error correction. And we calculate it using errant. And we use the correction score and not the detection score because it is important for us to actually, for the model to be able to correct the grammatical error mistakes and not just detect them. For simplification and coherence, we use SARI, which is again, a widely popular metric, which is used for text simplification systems. Paraphrasing is actually a little bit tricky. For that, we use BLEU score, and we use both reference-free, which is also called as self-BLEU in literature, as well as reference-based BLEU scores, because we feel that together they give a good picture of how paraphrasing is working, rather than just using one alone. Okay. Now this is the evaluation of our models, and this is how the performance looks like. All the models that begin with Spivavtor are the ones that have been instruction tuned. And on the columns, you can see the type and the size of the models, as well as the 4 different tasks, which is an aggregated performance and which has been scaled between 0 and 100 for comparison. Now, let's talk about each one of them in detail with our learnings. So these are the 4 learnings that we have come up with. So let's talk about each of them in detail. So learning number 1 is that Spivavtor models generally outperform the baselines. So it's clear to us that the Spivavtor models are, across all the tasks, they have performed better and significantly better than baselines, which demonstrates the usefulness of instruction fine-tuning for these text editing tasks. Learning number 2 is the fact why we introduced UAlpaca, where we wanted to compare the models empirically against a model which has been trained on diverse set of instructions versus very task-specific instructions, and we can see that the Spivavtor model outperforms UAlpaca by a huge margin, indicating that domain-specific instruction tuning outperforms large-scale diverse instruction tuning. Learning number 3 is that for our text editing tasks, encoder-decoder models actually outperform the decoder-only models. And this is a learning this is an empirical learning which has just worked out better for us. And this is just an average performance of encoder-decoder model is actually better than just the decoder-only model. And then the last learning is that within a same architecture family, larger models with more parameters, they actually have a better performance than smaller models, indicating the usefulness of adding more training data for these tasks. And the last one is a task ablation study where we held out a particular task and then compared the model performance on the held out task and found out that the model actually has a poor performance in zero-shot setting. So it does help the model to give a task-specific data and train with it. Qualitatively, our model doesn't suffer from the same problems as the OpenAI models, which are around task refusal or explanation of edits made and all, but it suffers from different kind of problems, which we have evaluated using native Ukrainian speakers. And some of the limitations of our models are that we are using a translation API, so our quality is limited by the translation API. The scale of the dataset could be improved. We could do more hyperparameter search since we haven't exhausted it completely. And we are aware that the OpenAI model's performance does vary with time, and it can keep changing in the future. We have released our best performing models and our data set to Grammarly's Hugging Face collection. And you can scan this QR code to actually download the models and give it a try. as well as the data sets which are actually publicly released. And if you have any questions, please contact the Spivavtor team. Thank you so much for your time and attention.